My name is and I will start first. In this project, we focus on the design and simulation of two types of full wave rectifier. The first one is a controlled rectifier with an R load and second is uncontrolled rectifier with an R load. Both circuits were simulated using LT-SPICE to analyze their performance under identical input conditions. The objective was to evaluate and compare the output characteristics such as the RMS output voltage, peak output voltage, current and power factor between the two rectifiers. The control rectifier was designed using a phase control silicon control rectifier SCR, while the uncontrolled rectifier used standard diodes. The results showed that the control rectifier provided a smoother DC output with reduced ripple compared to the uncontrolled rectifier. Additionally, the control rectifier had a power factor closer to unity, indicating higher efficiency. The simulation results were also compared with theoretical values, and minor discrepancies were found, which can be attributed to component tolerance and simulation settings. This study demonstrates the advantages of using control rectifiers to improve the quality of DC output in power conversion system.
Rectification is essential in power electronics because it converts alternating current into stable direct current, which is needed to power device, automation system, and variable speed drive, ensuring reliable and efficient operation. Rectifiers can be uncontrolled using simple diodes for basic AC to DC conversion, or controlled using SCR to precisely regulate the DC output for applications like industrial automation and variable speed drives. The performance of single-phase full-wave rectifiers with resistive loads can be analyzed using simulations, measuring key factors like average voltage, RMS voltage, ripple, and efficiency to determine which type is the best for practical applications. This assignment studies full-wave control and uncontrolled rectifiers with a resistive load to understand how each component affects output voltage, current, and power factor using LT-SPICE simulations.
Hello, my name is Nur Amira Najihah binti Muhammad Razi. Now I will go through the design assumption. Firstly, we assume all components in the system such as diode, SCR, resistors and voltage sources are ideal. This means there is no voltage drop, leakage current, parasitic effect or power losses in the component. Next, the AC input supply is assumed to be a pure sinusoidal waveform of 120 VRMS at 50 Hz with no noise, distortion, or voltage fluctuation. This ensures stability and efficient power transfer. Thirdly, the load resistance is assumed to be purely resistive and constant at RL 20 ohm throughout the simulation. This helps to maintain stable conditions during the analysis. For the rectifier, the full wave control rectifiers operate with a firing angle of 60. Meanwhile, the uncontrolled rectifier conduct naturally using diode without any control. Next, the system operates under steady-state conditions, meaning transient and start-up effects are neglected. This implies that we won't see significant changes during system startup or minor disturbance. Additionally, we ignore temperature effect on component characteristics, meaning temperature does not affect the performance of the component in this simulation. Finally, the LT-SPICE simulations are assumed to be accurately represent ideal operating conditions with no software limitations or numerical error. Therefore, this simulation depicts an idealized perfect operating environment. In conclusion, these design assumptions have been made to ensure that the simulation runs smoothly and accurately. With this assumption in place, we can ensure that the results obtained are stable and reliable for further analysis.
Assalamualaikum. My name is Muhammad Shakil bin Muhammad Noor. Matrix number B122310646 from BERG, and I will be explaining about calculation for uncontrolled and control rectifier. So for the uncontrolled rectifier, first we calculate for the RMS output voltage and current. Also for the ideal value, V out RMS equal to Vm over square root 2 equal to 169.71 over square root 2 equal to 120 volt. So for Is RMS equal to I not RMS equal to Vm over R equal to 169.71 over 20 ohm equal to 6 ampere. So for the practical, which is the simulation value, V not RMS equal to 168.31 over square root 2 equal to 119 volt, while for the I not RMS equal to 119 volt over 20 ohm equal to 5.95 ampere. So the second one, we calculate for the peak output voltage and current. Ideal value for V dot peak, which is equal to Vm equal to 120 VRMS times square root 2 equal to 169.71 volt. For the I naught peak, which is equal to V naught peak over R equal to 169.71 volt over 20 ohm equal to 8.49 ampere. So for the practical value, simulation value, so V naught peak equal to 169.71 minus 1.4 volt equal to 168.31 volt. This is because the silicon diode drop of 0.7 volt per diode, so is 2 diode times 0.7 equal to 1.4 volt. So for the I naught peak equal to 168.31 volt over 20 ohm equal to 8.42 ampere. Sorry. The last one, we calculate the power factor, which is equal to 1.0. It is unity, because since the load is purely resistive, which is 20 ohm, and the circuit is uncontrolled, the current drawn from the source is a pure sine wave that is exactly in phase with the voltage. There are no phase shift and no significant harmonic distortion in the source current. So we continue for the calculation for control. First one, we calculate the RMS output voltage and current. So the V no RMS equal to Vs RMS times square root 1 minus alpha over pi plus sine 2 alpha over 2 pi. So the alpha given is 60 degree. So we change from degree to radian, which is 60 over 180 times pi equal to 1.047 radian. So we insert the value 120 times square root 1 minus 1047 over pi plus sine 2 alpha over 2 pi equal to 107.64. So for the I naught RMS is equal to V naught RMS over R equal to 107.6 volt over 20 ohm equal to 5.38 ampere. So the second one, we calculate the peak output voltage and current, the same with the uncontrolled one. So the V ideal value, the V naught peak equal to Vm is equal to 120 VRMS times square root 2 equal to 169.71 volt. The I naught peak is equal to V naught peak over R, 169.71 over 20 equal to 8.19 ampere. The practical simulation value, V naught peak equal to 169.71 volt minus 1.4 volt equal to 168.31 volt. So for the power factor is equal to V naught RMS over Vs RMS. The V naught RMS value is 107.61, 107.6 actually over 120 volt, and is equal to 0.90, which is lagging because the delay in the firing distort the current waveform even though the load is purely resistive.
Okay, today my name is Nagarajan. Okay, next this is the full wave uncontrolled rectifier using 4 diodes. Previous for control we just use SCR. So for uncontrolled we using diodes. So from the output waveform, okay, a second. Okay, from the output waveform, the peak output which is confirming that rectifier affect the peak value in the starts immediately at the zero crossing. Both half-waves of input waveform fully utilized. As a result, the output plus setting the D waveform has no delay. Okay, and then the R is approximately 120, and the average voltage is at 108 volt. Okay, and then the waveform dissociate compared to the control rectifier. So uncontrolled. So wait a second. Okay, so this will be control and each of the waveform. This is the results. The simulation result shows that although the peak voltage remains constant under 70 volts for both rectifiers, the control rectifier allows the regulation of the output through this, and rectifier provides the higher and average output voltage of 108 volts, while control rectifier output is radial voltage, and therefore control rectifier are suitable for variable DC, whereas uncontrolled constant DC output is required. So that's all from me. Thank you.
Again, Nagarajan. My network number is B12231061. Okay, in this video, I will explain the simulation result of a full wave control rectifier followed by a full wave uncontrolled rectifier with a resistor load, which is all the values simulation are taken directly from the simulation waveforms, where the peak output voltage is under 70 volt. First this full wave control rectifier implemented using CSRs. Looking at the output waveform, we can observe, we can observe peak voltage, which is the same as the input peak voltage. However, unlike the uncontrolled rectifier, the waveform does not start conducting at the zero crossing. Conducting begins after the firing angle, which occurs cause a delay angle which are half of it. In this one, these outcomes, and some portion of the sine wave are missing, but the RMS output voltage is reduced to the exploratory 90 volts. And also the average DC output voltage is reduced to the exploratory 75 voltage. And last but not least, the waveform remains positive, but the contents reset in this part. Doctor, thank you.